Hello, what's up to you all matriculants? Welcome to This is Learn Extra. My name is Abraham, and you're probably wondering who's next to me now. Who's this guy? Well, next to me, it is a young scientist by the name of Raven. Raven, how are you?
Fine, thanks, and yourself?
I'm good, man.
Sure.
Tell the mindsetters about yourself.
Raven is an aspiring scientist. He's doing his master's in biology, specializing in microbial biotechnology. And I know you're wondering why I'm here. Well, I'm going to be representing South Africa at an up-and-coming science communication competition called FameLab in the UK.
Very nice, man. Congratulations.
Thanks.
How was the process throughout the competition?
Basically, there were regional rounds. I won the region in the Northwest Province. And then I went through to the nationals in Grahamstown. And now, after winning that competition, I'll be going through to the UK to represent South Africa.
Wow, nice one, and all the best there, representatives. Your last words to other mindsetters who are aspiring scientists and people would love to get into the competition maybe next year, also looking for what?
You know, science sometimes can seem a bit hard, but just hang in there. You get it at a point. It gets easier. Start off hard, gets easier. So just keep hanging in there and you'll make it.
Okay, but what was your secret in making it?
Secret? I don't think it's a secret. Everybody knows this. You know you can do your best. The only thing you can do is your best, so keep doing it.
Keep doing your best, mindsetters. What more can you ask for? But lastly, your shout-outs.
I'd like to make a shout-out to, first of all, the people who made me who I am. Bonata Park High School, big ups to you guys. I'd also like to send a shout-out to my friends in the Northwest, in Gauteng, and everywhere else around the country. Huge shout-out to Northwest University. Thank you. I'm here because of you guys.
Awesome, man. You're now famous. Hey,
thanks.
Take a high five.
Sure.
Well done, man. And to you all mindsetters, anything is possible if you believe in yourself. Nothing can ever be impossible. It's all in your mind. If you can think it, you can achieve it. Thank you so much, Raven.
Sure, Abraham.
Awesome. And now we have the other teacher. I nearly said the short teacher, but we have we have Tracy in the building, our teacher, who's going to be telling us more about what we're doing today. Tracy, how are you?
Yeah, thanks. I'm not sure what to do about that short comment, but I'll get over it at the time.
Cool.
Yeah.
Are you inspired?
Of course. Hello. This is very. I'm jealous. I want to get put in the logo.
No, I love it if it's a positive jealousy, hey?
Yeah, no, I could fit, Shirley. Just fold me in half. I could fit in.
Tracy, okay.
Moving on. Okay.
Stick to what you know best. What are we doing today?
Okay. Well, today, guys, we're going to look at rates of reaction. It's a really nice section, one of those sections that you guarantee to get, and it goes on to equilibrium. And in fact, we're going to have some fun just now.
Are you sure?
Yes.
Because I'm a bit ready.
Yes.
I didn't say I'm bored, but you know, when it's physical sciences, it's all about being active.
Yes, no, this is going to be lots of fun. And
okay,
we might make a mess.
All right, enough said, Tracy. You know, you're making me. Mindsetters, well, I can't really wait for this. All you need to do is download your notes on facebook.com/learnextra. There's a link there. Click on it to get to your notes. Either view them or download them. And you could be part of this lesson. But otherwise, Tracy is also going to tell you about the challenge question that we have for you guys.
Okay, so should we get going?
Yeah.
Okay, there we go. And I've lost my notes. You see, this board doesn't like me. Anyway, so today we're looking at rates of reaction. And it really is as simple as it sounds. So what are we actually going to do? Well, the first thing is we're going to discuss a little bit on how to measure the rates of the reaction. Then we're going to talk about the factors that affect the rates of reaction. And then within the questions, we're going to look at what's known as the Maxwell-Boltzmann energy distribution curve, okay? Which is one of the, it looks more difficult than it actually is. It's not that bad. So the first thing is we're going to give you a bit of a challenge question. And this is trying to put your science into more everyday sort of things. And the question is, explain using the collision theory why it is better to add instant coffee to hot water instead of cold water. Okay, so there's some things that, so it's not just a multiple choice, it says using the collision theory, so there's an important thing here why we need to use hot water instead of cold water. And when someone like me who is a little bit of a coffee freak, that's a good thing to know, and cold coffee is really not nice. Okay, so let's go on to rates of reaction. So the first thing is, when we talk about rates of reaction, we really are talking about how fast the chemical change takes place. So that means we are going to measure how fast we use up the reactants, or we're going to measure how fast we make the products. And generally, they'll end up being the same depending on the reaction, okay? So that gets us to an equation of sorts. And I'm not saying it's a definite equation simply because the way we measure the rate can change from reaction to reaction depending on the type of reaction. And we'll talk about the things we can use to measure rate. But in general, the rate of reaction is the change in, remember, delta means change in, and then we've got square brackets over here. Okay? Now, those square brackets might be new, it depends on how far you are in your curriculum, but those square brackets are an accepted abbreviation for concentration. Okay, so what this first part is saying, that the rate of reaction is the change in concentration of the reactants divided by the change in time, or the change in the concentration of the products divided by the change in time. Okay, sometimes we can't measure change in concentration as such, we have to measure other things. Okay, so the things we can also look at are things like color. So we measure color change, so it goes from purple to pink, or it goes from clear to yellow, and we measure how long it takes for that color change to take place. We can measure the change in volume or mass. Okay, so that means, for example, if we're creating hydrogen gas, we can connect the gas to a gas syringe and we watch how quickly the gas syringe fills up. Or we have the container on a scale, would have to be an electronic scale, and we watch how, if there's a gas that's being created, how when the gas escapes, the mass gets smaller. Okay, so those are the ones we can do. We can look at measuring temperature, so we can see how the temperature changes. That's quite an easy one to use. Or we can use turbidity, which is it's an interesting word, and that just means cloudiness. Okay, the one you probably will discuss in class is the reaction with sodium thiosulfate. When we react it with hydrochloric acid, it forms sulfur. That sulfur is a very fine yellow powder, and we measure how long it takes for the solution to get to a certain degree of cloudiness, okay, over a period of time. Now, what causes the rate of reaction, or what causes a chemical reaction to happen, is determined by what is known as the collision theory. And the collision theory comes up over and over again. In fact, I've already asked you it in the challenge question. Now, collision theory is actually really, really simple, okay? Because it really only has 3 parts to it, 2 parts to it. Number one, in order for a chemical reaction to happen, the particles, the reactants, must collide. It's called the collision theory. That's why it's called the collision theory, okay? So that's the first and foremost. But colliding is not enough. There's 2 other things that need to happen. Number one, the collisions, we have to have effective collisions. How do we have effective collisions? They must collide with sufficient energy. So if they collide too slow, then they're just going to bounce off each other and off they go. They've got to collide with sufficient energy. That sufficient energy is activation energy, okay, which you've heard about before. Last year you did the energy potential diagrams and used those nice little hills, okay? And the activation energy is the original hill. And the second one is they must collide in the correct orientation. So when they come together, it's like a jigsaw puzzle. They can't just collide any old how. They've actually got to come together in a specific way, and certain atoms need to overlap before they'll actually break apart and form the new bonds. Okay, so collision theory is really important, and the things they want when we talk about collision is the fact that the particles must collide, they must collide with sufficient energy, and they must collide in the correct orientation. Okay, and when we talk about rate of reaction, we change the rate by changing the number of effective collisions. So essentially, we can do nothing about the correct orientation. We can't literally take a set of tweezers and manipulate the molecules because they're too small. But I can do stuff I can make them collide more often. And just in a stats point of view, the more often they collide, the more likely it is for the reaction to be effective. And that's what we want. We want effective collisions. And obviously, if I do something with temperature, temperature can also change how effective the collisions are, or how many effective collisions we have. Okay? Now, what that does is it brings us to our experiment. Are you ready to have some fun, Abram?
Yeah.
Okay, so what we're going to do... Always ready, hey?
Yeah.
Okay, so guys, what we're going to do, and I've done it again, is I'm going to go over here, and I'm going to put my lab coat on, simply because I don't want to get messy, and I quite like my shirt, and I've realized I probably should have had a platform here too. Let's not go anywhere. Yes, I'm as short as it looks. Anyway, so what we're doing is we're going to do a bit of fun experiment, and this is just really to show you some factors. So I want you to pay attention. And what we're going to, I'm going to leave this one for last, because that's actually the lights of, and that one, that's the fun one. So what we have here, and it's really simple, is I have some normal dishwashing liquid, and I have hydrogen peroxide. Now, hydrogen peroxide is a bleach, okay, and it's what you can use to bleach your hair. Okay, it's not a great way to bleach your hair because it damages and does all sorts of things. But what we're going to do is we're going to look at the reaction between hydrogen peroxide and the dishwashing liquid. If I was measuring this with a stopwatch, okay, because we need to have a time frame, I would be looking at the way I would be measuring in terms of what I said on the board, color, temperature, all of that. You're going to see that bubbles are going to be formed, okay? So what we're looking at is we would measure how much or how many bubbles, we can't count them, but a relative volume of bubbles that's formed, okay? So the first thing I'm going to do is I'm going to take 20 volume. This is 6% hydrogen peroxide per volume. So if this is 100 mils, only 6 mils are actually hydrogen peroxide molecules. The rest is water because you have it in solution. You can't have this 100% concentrated. And this is 40. This is twice as concentrated. So this is far more concentrated. So what we're going to do is we're going to take a little bit of this and we're going to add it. I'm just going to put that on that side there. And I'm going to put a little bit in there. And we're going to watch the reaction and go, well, that was not that exciting. So we look at it and we go, maybe there's some bubbles. It's a bit boring. So that was with the 20. Let's now see what happens when I use the 40. Okay, so this is double the concentration. From what I've been telling you, the reaction should take a little bit faster. And if we look very carefully, there are some bubbles, but I think they're asleep, so let's leave those there. Okay, so now I'm going to put the twice as concentrated in there, and look at that. Yeah, well, that wasn't all that exciting either. But if we leave it for a little bit, okay, so I'm actually gonna. So we're just going to do this. We're just going to shake it a bit. Just hopefully that helps. And even I'm just shaking it to help it a little bit. But you can see with the twice as concentrated, I am getting more bubbles than I have with the half concentration, okay? Still taking a while. I think they're actually asleep. But that's okay. So now what we're going to do. So that's concentration. What I wanted you to actually see is that the more concentrated it is, it goes a little bit faster. Not much, but it does go a little bit faster. So what we're going to do now, let me just close this properly. Hydrogen peroxide is volatile, and I want it to go anyway, is I'm now going to put the hydrogen peroxide in this one, okay, and I'm going to put some in that one, and I'm using the same concentration, okay, because what I'm going to do now is I'm going to see what happens with temperature. So here I have a beaker with ice, which obviously then means it's cold. So let's see if that helps the reaction at all. We're going to make that cold. This is a beaker with hot water, and in fact, this water is sitting at 41 degrees. So that's relatively warm. The ice is, we'll check that temperature in a second. I'm going to put that in the hot water, and we're going to see if that helps us get any more bubbles. Okay, I do think it's not the most exciting thing. And Abram right now thinks I lied to him. Because I said it'd be fun, and it will be fun. I'm not finished
waiting.
yet. And it's not disappointing. This is science, okay? And in science, well, as you can see, they don't even want to mix in the cold water, okay? They like going, so don't want to be friends at all in the cold water. Do it in the hot water, and I shake it up a bit now, because I just want them to mix a bit. You can really see it's going a little bit more cloudy. That is also something we could measure. You can see the difference. This is still a nice, pretty light green. This is now gone cloudy because they're actually mixing quite nicely. And we are getting more of a reaction. But, yeah, it's happening. It's better. It's not great, okay? 41 degrees probably wasn't as hot as we would have liked. It's been sitting there for a while. But now, because all of you are going, now we're fast asleep, Tracy. That was just horrific. No, it wasn't. We're not done, okay? I am true to my promises. Okay, you can see it's getting there. Much slower though, okay, in the cold water, much, much slower. The hot water, which is actually cooling down really quickly, okay, because it's winter and it's not that hot in the studio. So what we're going to do is we're going to put that over there. And we're going to come along to this one. And right now you're going to hang on, wait, Tracy, you're changing conditions. I am a little. I am. But there's a reason why I'm doing this. Because now I'm going to take the 40 volume, okay, again, and I'm going to put it into my... And I'm going to use a little bit more because I can. And right now, you guys are all like, really, Tracy? Haven't we just done that? Correct? Done that, been there, got the very boring t-shirt. Okay. Wow. Now, what I have in my jar is potassium iodide. And I'm going to take some potassium iodide powder. Okay, some granules. And I'm going to put some in there. Oh, wait. You watching? Look at that. Same reaction. This was exactly the reaction I was hoping to get with the last one. But this has gone a whole lot faster. Okay? And it's a bit gross. Okay? Why did I want this? Because this is what I was hoping to get with this, just in a smaller volume. I'm not getting it because it's taking so long. I get it here because I've added a catalyst. Potassium iodide is a catalyst, okay? And in fact, this is also known as elephant's toothpaste.
Really?
Yeah, that's the name that some scientists give it. It's elephant's toothpaste. It's going to go for a while, and it's actually going round the measuring cylinder a little bit. But we made this, okay? See those little bubbles there this is the hot one, by the way. That's what we were going to get to eventually. This is just going to take a lot longer. Potassium iodide, a catalyst. It's not taking parts in the reaction. It's just helped it go along. Okay, so what I want you to think about are the things I changed, and then we're going to take a short break, and then we're going to discuss the factors involved in a chemical reaction.
Awesome.
Rate reaction.
That was a fun one. Hey, Tracy. Thank you. Well, thanks, my sisters, for tuning in. Also, we'll see you after the break. Welcome back, my sisters, and let us know, did you enjoy Tracy's experiment? And do try it and let us see what you get. What do you think, Tracy?
They can try it, but they're not going to be able to get the potassium iodide.
Okay.
But you can get hydrogen peroxide at a chemist. You can get the dishwashing liquid from home, and you can actually try different concentrations because you do get much more concentrated hydrogen peroxide as long as you're careful.
Awesome.
Just saying. Yeah.
But one thing that I'm definitely sure that you can try, it's the challenge question, and we'll answer it later on.
Yes. Okay. So the whole point of what we're doing there is to look at the factors of rates of reaction, okay, and what determines how fast it can go. The first factor is the nature of the reactants. Some substances are just naturally more reactive, which is something you've been looking at since grade 8 and 9, okay? And in grade 10, you even looked at different, you looked at valencies and all sorts of things, and just because of the structure of an atom, it is naturally more reactive than others. That's just the way it is, and there's absolutely nothing we can do about that. The next one is the concentration of the reactants, which is what we try to show you. The more concentrated the reactants are, and this specifically refers to to liquids and gases, okay, solutions. The more concentrated the solution, the higher the rate of the reaction, because when the solution is concentrated, we have a lot of particles available. And as soon as there's lots of particles available, there's more collisions that can take place, and the more collisions there are, the greater the number of effective collisions, so it increases the rate. And obviously the opposite is true if we decrease the concentration. The next one is surface area or reaction surface area, which is what I didn't do that here. That affects solids, okay, and that is the reaction where I take something either as a solid piece, a big chunk, or as a powder. As soon as we make something into a powder, it reacts faster because the total surface area has increased. There are actually more molecules that are exposed. The more particles that are exposed, the more of them can take part in the reaction. The more collisions we have, the more collisions we have, the more likely they are to be effective, therefore the rate increases, okay? The next one is temperature, which is what I showed you as well. Temperature affects the average kinetic energy of the particles, okay? So if I increase the temperature of the system, we increase in the average kinetic energy. That means more particles have lots of energy, which means more particles, have sufficient energy, okay? If they have sufficient energy, then the reaction can take place. So the higher the temperature, the more particles have sufficient energy, or more than sufficient energy, the more or the greater number of effective collisions we're going to have. Okay, so that's that one. And then the catalyst. Now you saw that really nicely before the break. What a catalyst does is it lowers the activation energy, so it makes it easier for the reactants to go from reactants to products. Okay, catalysts do not take part in the reaction. They start and end the same. They might change phase a little bit, but they don't actually take part. They simply add a certain amount of energy to the system, or that's the way you can think about it, which lowers the amount of energy needed for the reaction to take place. And if we lower the amount of the energy to take place, the more particles will have enough energy. Okay, so that's a fairly straightforward thing. Now, for all of these, okay, learn these, because this is the way your questions are going to get asked, is about these influences. Now, to go through the Maxwell-Boltzmann curve, we're actually going to look at question 1 of the test of your improve your skills, because this is where it's at, and it's always good to see it in context. So they tell you a catalyst speeds up the rate of a reaction. This behavior of a catalyst can be explained in terms of the activation energy and the collision theory, putting it into context for you. The first thing they tell you is the diagram below shows the Maxwell-Boltzmann distribution curve for a certain reaction. Guys, don't get too stressed about the Maxwell-Boltzmann part of this. That's named after the scientists who dealt with this, okay? That's the only reason why it's there. It doesn't mean anything, but it's named after people. So what this curve tells me, okay, is it's always going to have the shape that it's on here. It just either might go up higher or it might go out wider, okay? Your y-axis is what we call the number of particles. Sometimes it's called the fraction of particles. But pretty much this represents a number. So 10, 20, 15, 34,000. And of course, we're not too concerned about that because we don't ever want exact values. So from this graph, you are not going to get asked to do any sort of calculations at all because you can't. All right, the maths is way too difficult, and you don't do the right maths at school level anyway unless you do AP maths. So please don't stress about it. Along the bottom, along your x-axis, that's your energy of the particles. That represents the kinetic energy, so that's kilojoules. And what this graph does, this is not time, okay? So please, this is where it's different for you guys. You have to look at the graph in its entirety. The area under the graph, if I had to work out the area under the graph, that would give me the total number of particles in the system, okay? So the area represents the whole number of particles. Now, if we look at the graph over here, at this point here, that would be the maximum kinetic energy any particle has, okay? Well, sorry, not the maximum. That represents the highest fraction, I apologize, biggest number of particles. So this could be 20,000, 30,000, 40,000, whatever the case may be. That number of particles has whatever that energy is. And more than likely that you're starting to feel this temperature as the temperature, okay? As we come down here, the graph over here now gets lower and lower and lower because less and less particles have a high energy. Okay, have lots and lots and lots of energy at this whatever this temperature is, okay? The activation energy is here. This is a set value. Now, the activation energy is 300 kilojoules, 400 kilojoules, 750, 10, depends on the reaction, okay? Any particle that goes to the right of this graph over here has enough energy. So that in this particular case, there's only a small number of particles that have enough energy for the reaction to take place. Anything to the left doesn't have enough energy, okay? Does not have enough energy. So a large portion doesn't have enough energy. This would probably be quite slow. We're going to come back to the graph in a second. So the first thing they say to you, explain in terms of the collision theory and activation energy how a catalyst influences the rates of the reaction. Well, I just said that to you. A catalyst lowers the activation energy, okay? So if we now look at the graph, and let's take away, I'll do another color. What that means is if I have to draw in where the new activation energy is and say it's over here, and this area under the graph has now got bigger, that means there are more particles with sufficient energy for the reaction to take place. Okay, so what does a catalyst do? It lowers, okay, I'm going to do this in point form for you. So it lowers the activation energy, which we will write as EA, okay, which means we increase the number of particles with sufficient energy, okay. And I'm using these terms very specifically, guys. The collision theory says they must collide in the correct orientation and they must collide with sufficient energy. So I've got to use those terms, okay? We're ignoring the correct orientation right now. So we're increasing the number of particles with sufficient energy, and that means that we will have a greater number of effective collisions, which means the rate will get faster. We have a greater number of effective collisions, okay? Now they say to you, redraw the above distribution curve and show the new activation energy when a catalyst is added to the reaction mixture on the diagram. I've actually done that already. In the actual exam question said, redraw it in your answer book. Guys, you must redraw it as it's given, within reason, okay? They're not going to go and measure and say, well, is the area the same? Guys, within reason. But what does that mean? This original activation energy must be shown. That's included in the original graph. If you don't show that original activation energy, how's your examiner going to know that you understand that the new one is to the left? You've got to have the original to show where the new one is. And then you would label this and you would say, so you would put it here and you would draw a line and you would say new activation energy with catalyst. Okay, label it. Give detail. Don't assume anything. Do not assume that your examiner is going to know what you mean, because they might not. Okay? So we've done that one. Oh, I love this question. Okay, it's one of those questions where you should look and go, really? When milk is left at room temperature, it spoils rapidly. However, in a refrigerator, it stays fresh for a longer time. Use the collision theory to explain this observation. What are we saying? We've got room temperature, that's a temperature, and we've got a refrigerator. So we're going from a warmish environment to a cold environment. In a refrigerator, we are decreasing the temperature. By decreasing the temperature, we now have fewer particles with sufficient energy. Therefore, the number of effective collisions is smaller. Okay? In a refrigerator, we're lowering the temperature. Okay? That means there's fewer particles with sufficient energy because the kinetic energy of the system is getting smaller. Okay? Smaller number of effective collisions. Please remember, guys, that the definition of temperature is a measure of the average kinetic energy of the particles. Okay? It's a measure of the average kinetic energy of the particles. So whenever we talk about changing temperature, we're changing the kinetic energy. Increasing temperature increases kinetic energy. Decreasing temperature decreases kinetic energy. Okay? That's actually such a nice question because this was for about 7 or 8 marks. Nice one to do, okay? And they really are tending towards doing these. Question 2, and this is when I really hope you've managed to download the notes. It is long-winded, okay, but that's how your chemistry questions are going to be asked. Do not be put off by that, and read all the information because you're going to need it, okay? They tell you the active ingredient in a certain antacid tablet is the carbonate ion. This ion reacts with the hydrochloric acid in your stomach according to the following reaction. So we have the carbonate, CO3 2- plus HCl gives me Cl minus H2O plus CO2. Okay. The formation of the CO2 gas is an indication that the acid has been neutralized, and this brings relief from indigestion. You did learn in grade 10 that an acid plus a carbonate gives me a salt, water, and carbon dioxide. And in fact, the carbon dioxide is what makes you burp. Shh, don't tell anyone. After you've had the antacid, okay? And there are some people who think that the bigger the burp, the better the antacid tablet. Not necessarily, okay? In fact, bicarb is a very good, it's an it's a mother's home remedy type thing, but it works. It just tastes really bad. Okay, so a group of learners used 2 of these antacid tablets, so use the same ones, to investigate one of the factors that influence the reaction rate. They follow the method and use the apparatus given below. So we really want to find out what this one factor is. They say they place 1 antacid tablet in a conical flask, add 20 centimeters cubed of hydrochloric acid. Simultaneously, they stop the stopwatch, close the flask and the rubber stopper that is at the end of the delivery tube and attach it to the gas syringe. They measure the volume of the CO2 gas formed at intervals of 30 seconds, so they're measuring how the syringe increases, and then they repeat 1, 2, 3 above and grind the second antacid tablet to a fine powder. They're repeating all the steps. Temperatures staying the same, concentration staying the same, they're changing surface area. Surface area. And you know what? Write a little note for yourself. I now know what they're looking at. So here's our diagram, okay? And what we have is we have our conical flask, the antacid tablet, delivery tube, stopwatch, retort stand, gas syringe. We're all happy. Okay, we've read through all the information. Let's go to the questions. First one, define the term reaction rate. Brilliant. We've now made a list of all our definitions in our studies, and we go, well, reaction rate is it's a measure of the change in the concentration of the reactants or products over time. Okay, so the reaction rate is a measure of the change in of concentration of reactants or products over time, or per unit time, over a period time, anything like that. Perfect. Ooh, the questions we all like. Write down an investigative question for this investigation. Grade 12s, I'm guaranteeing you a question where you either have to write down an aim, a hypothesis, an investigative question, or a conclusion. They all 4 of those things have the same conditions. You must show the independent variable, the dependent variable, and the control. Okay? You must show the control. So dependent variable is the thing you're measuring. We're measuring rates of reaction. Independent variable is the thing we're changing, surface area. Control, we're keeping the concentration of the acid the same, the type of antacid, tablet, temperature, all of those sort of things. So when I write this question down, it cannot be a yes-no question, which means you cannot start the question with does. Does the surface area affect the rate of the reaction provided all other conditions are kept constant? Yes. No, not the question. Okay. Is there a relationship between? Also can't be the question you asked, because the answer is a yes or a no question. You must start these questions with either what is, okay, or how does. So you're going to start the question with how does or what is. Your choice, okay? I would start with how does, and you would do something like, how does surface area, let's start it with an S, not a U, how does surface area affect the rates of reaction Okay, we've got our independent, dependent variables. Okay, provided all other conditions remain the same. Now, the only reason why I'm saying that is because there's actually a lot of controls. So we've got to keep the volume of the HCl the same. We're keeping the concentration of the HCl the same. We're using the same antacid tablet. Sorry, we're using the same mass of antacid tablet. So there's a lot of controls in this one, which is why I'm saying that I provide all the other conditions stay the same, which of course you can't read, but let's just pretend. And in fact, let's just quickly write down those controls that I just said, because that's the next question. What are the variables that need to be controlled? Well, one is temperature, by the way. We really need to do this at the same temperature, so we're going to say temperature. The volume and concentration, we're going to do it this way, of the HCl. Okay, so it's going to be square brackets. The mass of the antacid. No, that's spelt wrong. Wow. Do you want to see that English isn't my strong suit? There we go. Antacid. Okay, those are the three most important ones. We are going to assume we're using the same one. Okay. Then, apart from the apparatus illustrated above, the learners need to use at least 2 other pieces of apparatus. So, we need to take a bit of a break. So what I'm going to ask you to do is quick look at the apparatus again, and during the break, you're going to actually think about what the 2 extra pieces of apparatus would need to be.
Awesome. And we also are going to be answering the challenge question after the break and announcing our last week's Test Yourself winner. So stay tuned. Welcome back, Mindsetters. Now, I hope you're enjoying our lesson, and keep those questions coming, because I see you guys are struggling there and there, but also helping one another, which is the spirit we up for as Mindsetters. Hashtag working together. Well, now it's time for me to announce our winner for last week's show. And our winner for this awesome Case Your Calculator is, drum roll please. Are you asleep?
No, well, no, it's been a long day, man. Stop it. And you asked me to make sound effects. I'm a science teacher.
Sorry, Tracy. Well, our winner is Ambition Shitsunzuko. Congratulations to you, Ambition Shitsunzuko. Can you say that, Tracy?
Ambition?
Yeah, Ambition.
Such a nice name.
Yeah,
I'm not
Shitsunzuko.
No, I'm not butchering your surname.
All right.
That's
Well,
not nice.
Well, for you guys to stand a chance, also I'll post the Test Yourself question links on Facebook, so do check it out. All the best.
Brilliant. And guys, Abram. See, anyway, sorry. Abram says you guys are struggling, which I know you are. This isn't the easiest section, but this is about practice. I promise you, the more questions you do, the more you're going to see they're all the same. They ask you the same thing over and over and over and over and again. And in fact, you can summarize the whole of rates of reaction into one page. Then you know it, because that's all it is, and then it's practice. Okay, so the question was, what 3 pieces of equipment would we need and why? Now, the first thing we'd probably need is something like a mortar and pestle, okay? Or, and if you didn't know what that means, something that you can grind the antacid tablet with. Okay, that's why you had to explain what it was used for, because in the question we go from it being in a solid to being in powder, so we need to be able to grind it. That's the first thing. The second thing we would need is a scale, because we need to keep the mass of the antacid tablet the same. Okay, so we'd need a scale to double check and to make sure. Okay, and the third thing we would need is a thermometer, because we want to make sure that the temperature remains constant. And by temperature remaining constant, I'm talking about the starting temperature. This is an exothermic reaction, which means the reaction is, as it takes place, will get hotter. But I don't care if the temperature changes during the reaction, it's the starting temperature that's important. Okay, then, what do they ask us after that? Then they say to you, the learners measure the volume of the CO2 gas formed in 30-second intervals in step 3. Write down the name of the apparatus that they used for measuring the volume. So we go back here, and we go, well, where are they measuring the volume? This one's a bit of a giveaway, because it's here. with the gas syringe? Look back at the question, okay? They didn't ask you to make it up, but it's in the gas syringe. Now, for those of you who have never seen a gas syringe, which probably is a lot of you, in fact, even my school, and I'm actually at a very quite a good government school, we don't have one anymore because they break, unfortunately, and they're very expensive, the new ones. It's a syringe, like a normal syringe that you use injections for, but it's really, really big, and it's made out of glass, okay, and they're normally about that long, and it's made out of tempered glass to help. And what you do is you line the edge and you seal it, but you also make the inside, but you seal it with like Vaseline, which allows it to actually move the plunger part to actually move, okay? That new glass gas syringes are very expensive, which is why we won't ever replace them. We find other ways you can use. Instead of a gas syringe, another way they could ask you is we could actually turn a gas measuring cylinder, like the plastic one we use now, fill it with water, turn it upside down in a bowl of water and make the gas go underneath and up and push the water down. It's another way to do it, which is the way we would do it because we have that equipment and we can get plastic gas measuring cylinders, which of course are cheaper, last longer when they fall on the floor, which happens because accidents happen, they don't break, which is always a bonus. Okay, so then they say, consider the sketch graph below. Now, this is a rate graph, and what it does is it shows the rates of the reaction between the hydrochloric acid and the solid antacid tablets. Rate is 0 when we start because there was nothing there. We put the tablet in, and then the rate increases. This is a steep gradient. The steeper the gradient, the faster the reaction is happening. Starts to slow down, so the gradient gets less and less steep. Why? Because we're using up the reactants. The less reactants we have, the less collisions there are. The less collisions there are, the slower the reaction. Till eventually it goes flat. When it goes flat, the reaction has reached completion. Everything's being used up. No more reaction happening. Okay? They say to you, redraw the above sketch on the graph. You would draw it on your paper. I'm going to do it on here. On the same set of axes, sketch the curve Q that was obtained with powdered antacid. Now, we've just said, well, with the powdered antacid, powder increases surface area. Increasing surface area means there's more collisions available for bonding. The more collisions there are available for bonding, the more collisions will take place. That means there'll be more effective collisions. The reaction rate increases. So that means my reaction rate increases, but I use the same amount of everything else. Eventually we'll go to the same place. It must finish in the same place. Guys, that is graph Q. You must label it, and you must have graph P on your original graph. Otherwise, there's nothing to compare it to. Make sure they are labeled. Very, very important. All right. The instruction on an antacid packet recommends that the tablets must be chewed for faster relief. How can chewing the tablets help? Okay. Some don't even ask you to chew them. Some you can dissolve in water. Or they come in powdered form already. I don't really like, and you drink. Why do you chew them? Because you're increasing the surface area. By chewing the tablet in your mouth, you're crushing it. By crushing it, you're increasing the surface area, and therefore it will react faster with the acid in your stomach. Okay, because you're increasing the surface area, which means there's more particles available for bonding. If there's more particles available, therefore there'll be more collisions. If there's more collisions, then more of the collisions will be effective, and it will work faster. Okay, so that means we need to go to the challenge question.
Yes.
Because Abby's looking at me like, I've got questions, we're coming. All right, challenge question, which actually wasn't so bad. If you've been listening to me, I'm pretty sure you guys, oh no, that was not it. Oh look, wrong challenge question. Wonder how that happened. Anyway, that's from something else. Let's go there. Okay, explain using the collision theory why it is better to add instant coffee to hot water rather than cold water. Well, if I add it to hot water, I'm increasing the average kinetic energy of the particles, the water and the coffee, okay? Increasing the average kinetic energy means more particles have sufficient energy. If more particles have sufficient energy, more or a greater number of effective collisions take place and the coffee dissolves faster. So simple as that.
Simple.
So always use hot water. Okay, and you know there's lots of theories about dissolving first in cold water, whatever. Moving on, to put it in hot water. Okay.
Well done to all the mind sitters that gave us their answers.
Yes, did they get it right?
Yeah, they did.
Yay!
Almost all of them.
Maybe it wasn't too much of a challenge question. We'll have to make it harder next week.
Maybe, but let's take their
Yes,
questions.
let's do some questions. Okay.
Right, on Twitter, we have a tweet from
Wow.
@formation.
Yes. We really are getting, we got we're
got
getting
a
tweets
tweet.
now too.
We've got a
Okay.
tweet from @formation asking for information. How does the temperature affect the rate of reaction?
Okay, it's what I've been saying, remember, and we'll just sort of do it in like quick. If I increase the temperature, what that means, and this is just in a symbol form, please don't write it like this, write it out in proper words in your exam, means that I'm increasing the average kinetic energy. Okay, so what that means is we increase the number of particles that have sufficient energy. Okay, and that's not hashtag for tweet, by the way, that's number. That's just what hashtag actually stands for. In fact, I don't even think it's called a hashtag, it's got another name. But we're not going to go there. Okay, so we increase the number of particles with sufficient energy. And as soon as we have more particles with sufficient energy, that means when they collide, their collisions will be more effective. Okay, so we're increasing the amount of energy in the system. Next one.
Cool. Priska saying, "Hala everyone. May I please ask what would happen in the reaction if we increase temperature, add a little catalyst, but reduce the concentration of the reactant?"
Wow, you want to change 3 things at once. Sweetie, that's a difficult one to answer because you're changing 3 conditions. In an exam, they will only change 1 condition at a time because it's very difficult to predict without having data to refer back to what would happen in that situation. Okay? So they're never going to go in one step, change temperature, catalyst, and concentration, because it's a difficult one to do, because even though I'm increasing temperature, which should increase the rate, if I decrease the concentration too much, it might cancel each other out. Okay? So there's nothing that says that temperature is a more important factor than concentration, or even that by adding a catalyst, that it's necessarily going to increase the rate a lot more than by decreasing the concentration would decrease the rate. So they're only ever going to change 1 condition at a time and ask you to compare 2 experiments where they've changed temperature, or 2 experiments where they've added a catalyst, or that sort of thing. So only 1 thing at a time. That's a difficult question to give a specific answer to. Yeah.
Okay. Prince asks, does volume have an effect on the reaction?
Good question, sweetie. Volume only affects gases, okay? And it affects gases in the sense that if I decrease the volume that a gas is sitting in, then the gas increases concentration, okay? And then it follows like all the others. If we increase concentration, we increase rate. If I increase the volume that the gas is in, then it decreases concentration because we have the same number of particles in a bigger space. By decreasing concentration, that means I'm decreasing the rate. So I didn't actually mention it. Well done. That's a very good question, but only for gases. Has no effect on solids and liquids. Volume. Okay, specifically. Yes.
Okay. What do they mean when they say something is in a room temperature?
Room temperature is around 20 to 25 degrees Celsius. They're just saying normal everyday temperature. It's just to give you an average sort of temperature, and it's about 20 degrees. Of course, that wouldn't be room temperature in South Africa, but it's just it's just a way of talking about it. It's so that it's not extreme temperature. We're not talking about hot temperatures, and we're not talking about low temperatures. Okay.
Okay. Here's another one. Can you please explain in terms of collision theory why the rate of chemical reaction increases with increasing temperature?
Okay, I've done that already. We're doing this lots, guys. Remember, increasing temperature increases average kinetic energy. Therefore, more particles have sufficient energy. If more particles have sufficient energy, they have more effective collisions. More effective collisions, reaction happens faster.
Okay. What happens when you're being asked to investigate the surface area? How will you know that you are supposed to investigate?
Okay. When it comes to surface area, it has to be a solid, first of all, okay? And then they'll do things like they'll say to you they have magnesium ribbon and then they have magnesium powder. So they tell you, or it goes from granules to powder, or it goes from a solid to powder. So they'll tell you that. They'll tell you that the state of the solid changes. Okay, and remember, as soon as it goes to powder, we increase the overall surface area. That means it's going to go faster. So that, like in the antacid question, they said to you they had one hole and then they crushed the second one. So I knew they were making it into a powder.
Okay. Sbusiso asked concerning our
Yes.
elephant toothpaste.
Yes?
He asked, is it solid?
No, it's a foam. So it's gas bubbles that have created the foam. So eventually it's almost like a liquid, okay? And in fact, it's quite gross now, and I'm glad I don't have to clean it up because now it's starting to sink a little bit because the gas is escaping. And talking about our elephant toothpaste, for those of you who want to try it at home, because you can't get potassium iodide, so listen carefully. You can either use yeast, okay? So if you bake bread, which I don't do because I can barely bake a cake, is you can use yeast in it instead of potassium iodide, or, okay, you can use chicken livers. If you chop up chicken livers, you can put some chicken liver in, and you'll get exactly the same reaction.
Wow.
So you can do it at home with those.
That's very nice.
Nice and easy and to the point, but that, of course, means that you have to
Is
use
it
chicken
easy?
livers. Of course it is.
Oh, it's easy.
It's home chemistry. You can do lots of stuff at home. Of course, it's fun.
Okay, last
Yes,
one. A
last
quick
one.
summary on the influences of the rate of reaction, please.
Quick summary of what?
The factors that influences
'Kay.
the rate of
Got
reaction.
download the notes because it's really easy. Nature of reactants, the type of reactant. Temperature, increase or decrease. The concentration of the reactants. The surface area. And the last one was whether you use a catalyst or not. So there's 5. Okay, they are there on the notes, and they're very, very logical. And they should be in your book somewhere, okay? Get the notes because it actually does explain a little bit more detail, and there's an extra question on there, okay? So guys, learn those. So the only ones we're going to do, and remember, concentration affects gases and solutions. Surface area affects solids. Catalyst affects both regardless. Nature of reactants, nothing I can do about that. And temperature affects everything, solids, liquids, gases, whatever the case may be. Okay, temperature is probably the one that's easiest to recognize. And that's starting temperature, not ending temperature. Okay, guys, practice, practice, practice. I'm going to have to say goodbye in a couple of seconds. And next week we're going to do equilibrium, which I know you guys struggle with. But hang in there. Practice, practice, practice. Okay.
Well, thank you so much, Tracy. Hey, nothing beats practice and more experiments.
Yeah, practice and go home and do this with yeast and chicken livers.
Awesome. Well, my sisters, we're only left with 20 seconds. On that, we just want to say, keep on believing in yourself. As you've heard from Revan, nothing is ever impossible if you believe in yourself. So whatever you think, you can achieve it. From us today, we just want to appreciate the time we had with you. Make sure that you get your notes on learn.mindset.co.za, and all the best for the competition that we have that is proudly sponsored by Kesho. And our last words, me and Tracy, we just want to say, we love you guys and peace.